that, I would get tension equals m2, oh, I don't know why I put that 2 there, m2g sine 35, and then that would be minus m2 times ax. Well, I know that tension, if I'm thinking about the second mass, equals this one. And I know that tension, if I'm thinking about the first mass, equals this one. And the tension in both of these that are attached to both of these blocks are equal to one another, because it should be the same tension. So I can take this equation and set it equal to this equation, because I know both of the masses. I know acceleration due to gravity. That means the only thing that I would have left to solve for is that acceleration. So let's do that. Okay, so that gives me, I would have m1 times ax plus m1g times sine 35. That equals m2g sine 35. There we go. M2g sine 35, and then that's minus m2 times ax. Okay, so I want ax on the same side, right? So if I did that, I would get m1 ax plus m2 ax equals, if I did my mg2 sine 35 and then my mg1 sine 35, if we went ahead and did those, we should get 45 newtons and then 19.7 newtons. So I would find here, this one would be, so 45 newtons for mg sine of 35, and then mg1 sine 35 be, if I brought that over, it'd be minus that, so minus 19.7 newtons. I could factor out ax, so ax, and then my combined mass would be 11.5 kilograms equals my 45 newtons minus 19.7 newtons. So if I take that divided by 11.5, I'll get my acceleration. We should get that to be 2.2. Okay, but they asked me to find acceleration first, but then in B they asked me to find tension. Well, we just solved for two, we rearranged on both objects for tension, so it doesn't matter which one we use. Let's go ahead and just plug it in for one of those tension equations that we already solved for. Let's just use, let's use our first mass. So we had m1 times ax plus m1g sine 35. So now I know the acceleration is 2.2. I know the mass of that first object we said was 3.5, so I could do my 3.5 times 2.2 plus my 3.5 times acceleration due to gravity times sine 35. And if I do that, we should get the tension to be equal to 27.4 newtons. Okay, so on these Atwood problems, we have to think about them separately. You need to think about them as separate objects. And as long as we know that, or we remember that they're accelerating together because they're connected. So this 8 kilograms was going to move, that block was going to move down the incline because it's heavier. So then that means the 3.5 is going to move up that incline. They're moving as a system, yes, but we can find them independently, or we can think about them independently to find acceleration and then to find tension. Okay, so I now want to kind of shift gears, and let's go from the Atwood's machine, but now let's add friction. let's add some friction here. So for this example, it says the following is a simple method of measuring the coefficients of friction. Let's suppose that a block is placed on a rough surface inclined relative to the horizontal as shown here. So we have our angle here. The incline angle is increased until the block starts to move. Show that you can obtain the coefficient of static friction by measuring the critical angle at which this slipping just occurs. So my goal in this problem is to find that the coefficient of static friction, so that mu s, coefficient of static friction, is somehow equivalent to just that angle theta. I need to figure out some type of relationship between these two. I need to prove that. So I know, if we go back to our picture, they gave us in this picture a free body diagram. So let's look at that one. Or let's just redraw it. So we have our angle. That's a really steep angle. I'm sorry, guys. And then we just have this block that's definitely not perpendicular to that surface. Let's look at all of the forces that we have acting on the block. So let's draw a free body diagram. I have the weight force, we know, and I also have the normal force that would be acting at an angle. And I also know that I have friction because they're asking me to find this coefficient of static friction. So I have friction acting along that incline. And since the box is going to move this way, friction is going to be acting in that opposite direction. So this would be the force of static friction. I set my axes same way here. Your book also, or the problem did that for us. So if I'm thinking about my components here for weight, because I'll have to break those up, then my theta would be right here. So there's my theta. So here's my free body diagram. I have the normal, I have weight, but then I have the force of friction that's keeping that box on the incline, and I want to know that this coefficient of static friction is dependent on here. So that means as I'm increasing that angle, when is that box going to slide off? So I need to show that there's a relationship between the coefficient of static friction and theta. Okay, so I know that the only real forces that would be moving then, or the direction that's going to have a direct effect on whether or not this box is going to start to accelerate, is the x direction, right? Because if it's going to accelerate, it's going to move down that ramp, which means that would be my x direction. So the only forces that I need to think about here would be my net force in the x direction. So let's write my net force in the x direction. So I have the force of friction, but then I also have my weight component, right, in that x direction. So I would have weight is also equal to m times g, so mg. So I have mg, and this would be sine theta. So I have mg sine theta, and then since that would be going that way, it would be a positive value, and then I would have a negative value because I'd be moving in the opposite direction, force of static friction. So I have mg sine theta minus force of static friction. Well, I can't set these, I can set these equal to 0 because right now I know that the block is at rest because it's static friction, right? So I know that this block is just sitting here at rest. So I could say that my net force, since the block is at rest, it's static friction, that would be equal to 0. So then I could say force of static friction equals mg sine theta. Okay, but they asked me to show that the coefficient of static friction is somehow related to this theta. And I don't see mu s in here yet. So I know that the force of friction is equal to mu, coefficient of static friction, times the normal force. So let's just go ahead and say mu s times the normal equals mg sine theta. Okay, well, I could also do some plugging in or substitution for N to really see that my coefficient of static friction is dependent on this angle here. So the normal, let's write our forces that are acting in the y direction. If I think of the sum of the forces acting in the y direction, I have the normal force, and then that would be minus the component of weight in the y direction. So that would be mg, so minus mg cosine theta. Again, if we're assuming that this block is at rest because it has static friction, then I could say these are equal to 0. So N equals mg cosine theta. I want to plug that in then right here. Mu s times mg cosine theta equals mg sine theta. No. There we go. So mu s times mg cosine theta equals mg sine theta. Guys, let me just rewrite that because I don't like that it's just kind of there in the middle. Okay, to see what coefficient of static friction would be equal to, then let's divide both sides then by this mg cosine theta. If I did that, I'd have my coefficient of static friction equals mg sine theta over mg cosine theta. What happens to the mg's? They cancel out. And sine over cosine, sine theta over cosine theta would just be tangent theta. So I can show coefficient of static friction equals tan theta. So this shows me that the coefficient of static friction is directly related to that angle of incline, of inclination. So we've just proved by using our net forces in the x and the y direction that coefficient of static friction is directly related to that angle, to that theta. Okay, let's actually do now, let's do another problem with friction. Okay, so let's say we have a hockey puck that's on a frozen pond and it's given an initial speed of 20 meters per second. If the puck always remains on the ice and slides 115 meters before coming to rest, we want to determine the coefficient of kinetic friction between the ice and the puck. So they actually gave you a free body diagram here in the object. We know that there's weight acting on the object. We know that there's the normal force. We have the ice pushing back up on the puck. I have the force of friction, and I know that it would be, right, because it's moving that way, so force of kinetic friction should be opposite to that. So let's just go back and let's kind of think about what we were given here. I know what they gave me. They gave me that it is traveling a distance of 115 meters. I know that its initial velocity in the x direction is 20 meters per second, and it's going to come to rest, so its final velocity is going to be 0. I do not know acceleration, and they're asking me to find mu. I want to find that coefficient of kinetic friction. Okay, so let's go back and draw our free body diagram here too. We had weight force, we had normal force, and then we had the force of kinetic friction. Okay, so there's our free body. So the only force that would be acting on this puck in terms of its acceleration wouldn't be normal or weight force, right? It's going to be my force of kinetic friction, because that's the only unbalanced force then that would be slowing it down or causing it to have that deceleration. So then that means that my sum, my net force, my sum of the forces in the x direction is just equal to a negative force of kinetic friction. And I know it's accelerating, so it's not equal to 0. I know it's equal to mass times acceleration in the x direction equals my negative force of kinetic friction here. but what does kinetic, or what does the force of friction equal? Because I need to find mu. So I need to make sure that I write this in terms of the coefficient of kinetic friction. So I have the mass times acceleration equals, I know the force of kinetic friction is the coefficient of kinetic friction times the normal force. Well, they didn't give me mass of this puck. So that's a problem because I don't know acceleration and I don't know mass and I also don't know mu, and that's what I'm trying to solve for. So I need to think about a different way that I could possibly get rid of the mass here of this puck because I don't have that at all. Well, I know that the normal force, since the object is only accelerating or decelerating in that x direction, the normal and the weight force have to be equal to each other, since it's not accelerating in that vertical direction. So I know the normal force equals weight, so normal must equal m times g. So if I look at this, then I could rewrite that. Mass times acceleration in the x direction equals a negative mu k times m times g. So if I wanted just that acceleration here, I could divide both sides by mass, and I would find that my acceleration in the x direction is equal to mu k times g. Okay, so my goal is to find mu k. That's my goal. And I have these other pieces here of this equation that they've given me. They've given me a horizontal distance, an initial velocity in the x direction, a final velocity. I have acceleration where I could plug or substitute that in here for acceleration. So, oh my gosh, let's use a kinematic equation, and then I'll bet we'll get what we want. So let's use Vf squared equals Vi squared plus 2a, and then that change in x, which would be 115. So when I have a, I'm going to substitute this in here for a, and let's just see what happens with that. So I know my final was 0, and then that's equal to my initial, which was 20 squared. And then plus 2 times my acceleration, which is a negative mu k times g, but g we know is 9.8, so let's just go ahead and write times 9.8. And then that's times my change in x here, which is, we can say that we started initially at 0 and then it moved 115 meters. So every single one of these variables will, the only thing I'd be left with is my mu k. So if I do my math here, I could solve for mu k, and then you should end up getting here, what, this would be like a negative 400 equals a negative 2254 times mu k. I think that's what I ended up with. And then I just divided that negative 400 by a negative 2254, and then that gave me my mu k to be 0.177. So there's my mu. So this would be, I think, I think it would be a more challenging friction problem. So we could do some easier ones, but I think it would be best if we stuck with maybe the more difficult ones at first. So we had one on the friction problem, the last one, where we're just using the symbols or the variables, and then we have one like this where they've given you pieces of information, and I'm still trying to use these symbols to get just an acceleration, and I know that now that I have this acceleration, because I know g, and I'm trying to find mu k, I could have used a kinematic equation, which we did here, to solve then for mu k. Tomorrow in class, we're going to do some practice with these friction problems. We'll do a couple maybe together, and then I'll have you work on some on your own. And then we'll do more practice on Wednesday for your test, which is on Thursday. Your multiple choice test will be Thursday, and I've decided on Friday you'll have your FRQ in class. So instead of taking it home, I want to make sure we can do it in class. And I will see you guys tomorrow. I hope you have a great night. Bye.